Alright, in this video I'm going to be working a set of 3 free response questions for Cal BC. They're going to be free response on calculator, so if you're working this for homework, you would have no more than 45 minutes for this. And the first one's kind of just like, here's a table, and I'm going to ask you some questions about the function that has this derivative that goes with the table. So f is twice differentiable when x is positive, f of 1 is 15, f double prime of 1 is 20, and we've got a table for f prime. We're going to start by writing an equation for the tangent line to the graph of f at x equals 1, and then using that point to approximate f of 1.4. Alright, so we're going to need a point. That would be x equals 1, f of 1 equals 15. Then we'd need a slope. Okay, f prime of 1 is equal to 8. So I can write an equation. Let's say y minus 15 equals 8 times x minus 1. And that's the first part, just write an equation for the tangent line. Then we're going to use that line to approximate f of 1.4. Okay, so if I want to do that, do an approximation. Really, I'm just looking for the value of y when x equals 1.4. X equals 1.4. Y is going to equal 15 plus 8 times 1.4 minus 1, and that's going to be good. Okay, I mean, we could simplify that if we wanted to. Maybe I will, because we can do 1.4 minus 1, that's 0.4 times 8 is going to be 3.2. Hey, but I could see people saying that's 0.32, like mistakenly, and so that's why I would recommend you just go ahead and say f of 1.4 is approximately equal to, but not equal to, 15 plus 8 times 1.4 minus 1. I'm just going to leave it like that. All right, now we're going to use a midpoint Riemann sum with 2 subintervals of equal length and values from the table to approximate this integral. Okay, now the first thing I'm going to say is like, okay, I want to be able to look at this. It's like, oh, I kind of want to just use the fundamental theorem on this. Say, okay, I know an antiderivative for f prime. That would be f, just plug in the bounds, f of 1.4 minus f of 1. And we know f of 1, but we don't know f of 1.4. Okay, so that's not going to be, a good technique for us. That's why we have to use the midpoint Riemann sum. And I guess we don't have to use a midpoint Riemann sum, but they specified, so that's what we're going to do. Okay. I think first, especially with a midpoint sum, I think it's good to map out the interval you're integrating over and think about where you're going to be getting your values from. So we're integrating from 1 to 1.4. Which means that if we're using 2 subintervals, that'll be halfway is 1.2. And if we want the midpoint of each subinterval, we're going to be looking at x equals 1.1 and x equals 1.3. Okay, so what we really want is to figure out, okay, I've got them right there. Okay, so it's going to be the integral from 1 to 1.4 of f prime be approximately equal to, okay, width of the first subinterval, 1 to 1.2 is 0.2. Height is going to be the representative. I get it, x equals 1.1, and that would be 10. So I can put that there. And then I'll be adding that to the next subinterval, also has a width of 0.2. And then I'm going to get my height from the value in the table. That's looking like 13. And there I've got myself an answer. Okay. And show the computations that lead to my answer. Those are them right there. Okay. If we wanted to, oh, wait a second. I only did the Riemann sum. So we're going to use the approximation to estimate the value of 1.4. Okay, so we are going to end up doing that. Okay, so integral from 1 to 1.4 of f prime, kind of like we were saying earlier. Probably the first thing you might think to do is that say, oh, that's going to be f of 1.4 minus f of 1. Okay. So if we wanted to, approximate f of 1.4, we know that f of 1.4 equals f of 1 plus the integral from 1 to 1.4. That's f of b equals f of a plus the integral from a to b of f prime. That's a formula we've used a lot in this class. Okay, and we've got an approximation for this integral right here, and we know the value of f of 1. So I'm going to go back over there and say, okay, f of 1 was 15. Okay, so I'm going to say f of 1.4 is approximately equal to 15. Wait, I'm just going to triple check that, yeah. Okay, 15 plus that integral, which we determined to be about 0.2 times 10 plus 0.2 times 13. Okay, and that's going to be our approximation. We showed the computations that led to our answer. We're good. All right, now we're going to use Euler's method starting at x equals 1 with two steps of equal size to approximate the value of f of 1.4. Okay. Oh yeah, I think I remember what the last one is. I think we're going to be using a second degree Taylor polynomial at the end. It's a good free response question, looking at all the different ways you could approximate the value of f of 1.4 from, given data. So if we're starting at 1 and we're trying to go to 1.4, we're going to take two steps of equal size. We're going to go 1 to 1.2 and 1.2 to 1.4. Right? So I'll start with this one. The first tangent line it's going to be, we already did this. We already wrote a tangent line at x equals 1. But just to remind you, point was 1 and 15. Slope was, I believe, 8. But I'm going to check again. Y minus 15 is 8 times x minus 1, yeah. Y minus 15 equals 8 times x minus 1. Okay, now with the first step, I'm going to say, okay, this was tangent line 1. To organize my work like that. And say, all right, step 1, x equals 1.2, y equals 15 plus 8 times 1.2 minus 1 is 0.2. Okay, now you can just kind of carry this number around with you and just keep using it, and it gets longer and longer in Euler's method. Me personally, I prefer to actually do the simplification. 8 times 0.2 is going to be 1.6, right? Because if you multiply something by 8, it has to get bigger. And it wouldn't be 0.16 because 0.16 is smaller than 0.2. All right, so 15 plus 1.6 is 16.6. Right, and then I'm going to have my second step for Euler's method is just going to be another tangent line. Tangent line number 2, I've got a point. X equals 1.2, y equals 16.6. Slope, I'm going to need the value of f prime of 1.2, but I've got that in the table, I'm pretty sure. Right? F prime of 1.2 is 12. Okay, so I'll write my equation for my second tangent line, y minus 16.6 equals 12 times x minus 1.2. Okay, and then I'll take my second step, x will equal 1.4 and y will equal 16.6 plus 12 times 1.4 minus 1.2. And you could just throw a box around that answer. I'm going to just kind of combine all of my work here and say f of 1.4 is going to be approximately equal to, all right, what would this be? 12 times 0.2 would be 2.4, plus 16.6 would be 19. Okay. But if you're cautious about that arithmetic, maybe rightfully so, feel free to not do it and just throw a box around your unsimplified answer. All right, and then write the second degree Taylor polynomial for f around x equals 1, and then we'll use that Taylor polynomial to approximate the value of f of 1.4. All right, so first I'm going to start out by writing the recipe for a second degree Taylor polynomial for a function around x equals 1. So that'll be the second degree Taylor polynomial is equal to f of 1 plus f prime of 1 times x minus 1 plus f double prime second derivative second factorial second power of x minus 1. Okay, that's going to be a second degree polynomial. Okay, stop there. Okay, not two terms, but till the second power term. And you know it's a second power term because it's a bunch of 2's, right? Second derivative, second factorial, second power of x minus 1. Okay, now I need to go and, kind of from the table and the statement of the question, get f of 1, f prime of 1, and f double prime of 1. We're going to need those. I think I already know that f of 1 equals 15, and f prime of 1 is 8. I just need to go look up f double prime of 1. They said it, yeah, f double prime of 1 equals 20 right there. So let's say, all right, 20 divided by 2 factorial is going to be 10 times x minus 1 squared. And so I'd say, f of 1.4 is approximately equal to what I would get when I plugged 1.4 into the secondary Taylor polynomial for f. So that would be 15 and 8 times 1.4 minus 1 plus 10 times 1.4 minus 1 squared, and that'll be my approximation, right? If you wanted to, you could figure that out, but I don't think that's the best idea ever, because there's no extra points for saying which one's the best approximation or whatever. That's kind of the whole point. Okay, these are different ways that we could approximate that value. So the next one, this is from a different AP exam, but this is a polar no calculator question. And I like this one, first of all, because it looks like the moon, and then also because it is telling you where the intersection points are. I really like that. Okay. So we know that this is theta equals pi over 3 right here. And we know that this is theta equals 5 pi over 3 right there. Okay, those are my intersection points. Okay, let R be the shaded region, write an expression involving an integral for the area of R. All right, now, looking at this, I can see that this is one that has two curves involved because there's R equals 4 and R equals 3 plus 2 cosine theta. There's two equations. And I can see there's two graphs, right? Two different polar graphs making this thing that looks like the moon. And then the question is, you may remember from when we studied polar curves and polar areas, is am I adding integrals or am I subtracting integrals? Is this a region that sits like properly between the two curves, or is it like handing off from one to the other? If I was looking for the region, I'll just erase this and get rid of it. If I was looking for this one right here, okay, that would be the type of integral where I'd have to add. But this one is not one of those, and I can tell that by drawing a line, like a radial line, from the origin to the edge of the region I want to find the area of. And if I'm hitting two different curves, you need to take either two different integrals and subtract them, or you need to just be subtracting because it's the area between those two different curves. Okay, so what you also need to remember is the formula for polar area, and so that's area equals 1/2 of the integral of r squared with respect to theta between two theta values. Okay, they gave us the theta values, so it's going to be 1/2 of the integral from theta 1 to theta 2 of, okay, on the outside, let's think, okay, we do have to figure this out without a calculator. Okay, the one that's kind of like wrinkled, that's got to be the one that's got a more interesting equation. R equals 4 is a very plain equation, so it should have a very plain graph. It's a circle centered at the origin with radius 4. Okay, so I'm seeing this one is r equals 4 right here. Should probably snap too, right? Okay, maybe not. And so that one is r equals 4 on the outside. So 1/2 r squared d theta, and we actually know theta 1 and theta 2. You know that's pi over 3 and 5 pi over 3. Okay, you can do that and subtract another one, but I actually don't recommend that anymore. I forgot about that. This year I've kind of like changed my tone. I really think you need to subtract them on the inside because if you don't have the d theta, then that could be troublesome for you. And I don't want you to be wrong on kind of a technicality with a differential thing when so often in AP Calculus that doesn't matter. This would be a situation where it does. Okay, so outside squared minus inside squared, r squared minus r squared d theta. Okay, and this one is a set it up and don't evaluate it, so like our form is going to be really important. And so that's r equals 3 plus 2 cosine theta. So 3 plus 2 cosine theta. Alright, and that's going to be an expression involving an integral that gives us the area. Now we're going to find the slope of the line tangent to this graph at theta equals pi over 2. Okay, and we know that this is one of those problems that involves quite a bit of algebra and definitely product rule. So we're going to need y and x, and then take the derivative of each of those, plug in pi over 2. It's going to be a whole process. So y equals r sine theta. That's something that's really important for us to know. Okay, so that's going to be 3 plus 2 cosine theta multiplied by sine theta. Okay, now in this case, I don't necessarily recommend distributing. Okay, I think you should just leave it into the product rule like as we're looking at it right now. In fact, I'll just take the derivative of y and get dy d theta, or y prime of theta, and I'll take the derivative of sine first and leave this thing in parentheses the same. And then I'm going to add, leaving the sine the same, taking the derivative of the thing in parentheses. So that would be negative 2 sine theta multiplied by sine theta. Okay, and then I might just go ahead and plug in dy d theta at theta equals pi over 2. And get, okay, 3 plus, alright, at pi over 2, let's draw a little circle here. That one was pretty rough. But the coordinates of that point are 0 and 1. So cosine of pi over 2, that's going to be 0, and sine of pi over 2, that's going to be 1. So it's going to be 3 plus 2 zeros multiplied by cosine, which is 0, plus negative 2 times 1 times another 1. Okay, so I'm going to get negative 2 there. Okay, then I might just go ahead and shrink that up a little bit and figure out the value of dx d theta at theta equals pi over 2. So x equals r cosine theta, and that's going to be 3 plus 2 cosine theta multiplied by cosine theta. Dx d theta, or x prime, is going to be, maybe I'll take the derivative of the thing in parentheses first, negative sine theta, leave that thing the same. Then I will, oh wow, didn't realize how little room I had over here. Maybe I'll just move it. Okay, and then I'm adding on, leaving the parentheses the same, taking the derivative of the other thing. All right, there we go. I don't know if you can still see that. Yeah, it's, there we go. I think that might, there we go. Now I'm going to plug in pi over 2 and get, okay, negative 1 times 0. So it's going to be a 0, plus 3 plus 2 zeros multiplied by negative 1. Okay, so it's going to equal negative 3. And since dy dx equals y prime over x prime, x at theta equals pi over 2 is going to be y prime divided by x prime, and then I'm just going to stop there. Alright, and then we're going to say a particle moves along a portion. Okay, so this is one of those problems that I actually focused on pretty heavily this year in my class. I'm not totally sure why, but I just decided to, I guess. And we did a bunch of these. So a particle moves along the portion of the polar curve between 0 and pi over 2. Particle moves in such a way that the distance between the particle and the origin increases at a constant rate of 3. And now we need to know what they mean by distance between the particle and the origin, and that's going to be r. And if r is increasing at a constant rate of 3, that means that dr dt equals 3. Okay, and we're going to find the rate at which theta changes with respect to time when the position of the particle corresponds to theta equals pi over 3. Okay, so we want to find, we'll just go ahead and maybe underline that. Okay, the rate at which the angle theta changes with respect to time at the instant when the position, okay, so at theta equals pi over 3. Okay, now what we've got is an equation for r and theta, and we've got dr dt, yeah, and we want d theta dt. So what we need to do is take the derivative of this original equation right here with respect to time. Okay, so r equals 3 plus 2 cosine theta. Now we're taking the derivative with respect to time. Derivative of 3 is going to be 0. The derivative of 2 cosine of a thing is negative 2 sine of that thing. And we keep the inside the same and then multiply by the derivative of the inside for the chain rule. And we're going to need to do that in order to get d theta dt to show up in this equation. Okay, but now we've got all the pieces we need. So we're going to say that dr dt, which is equal to 3, equals negative 2 times the sine of pi over 3. Okay, so we're going to think about that. Okay, let me draw a diagram for you. 3 pretty far up, that makes 30, 60, 90 triangle. That leg's going to be a half, and this leg would be root 3 over 2 because that's the longer of the two legs, because root 3 over 2 is the bigger number. So sine opposite over hypotenuse is root 3 over 2. Okay, so I'll be able to solve for this. Maybe I'll just kind of get rid of these. Divide both sides by negative square root of 3. That would be exactly what I want. D theta dt. And so d theta dt is going to equal 3 divided by the negative square root of 3. Indicate units of measure. Okay, I didn't notice that. So I'll do that last. And so, say, all right, I found that here. And then the units, okay, d theta dt, change in theta divided by change in time, that's going to be, okay, the units of theta is radians, always in AP Calculus. And units of time, well, they probably told me that seconds. All right, so radians per second. All right. And that's all for the polar problem. Now we're going to do another Taylor polynomial problem, or Taylor series problem. We're going to start by, we've got, actually, we probably should look at the given information. Okay, they're giving us the graph of y equals the absolute value of f's fifth derivative. We did this pretty recently. I told you, if you ever see them presenting you with the graph of an absolute value of a high order derivative, there's really only one thing that can mean. It means we're going to be doing Lagrange error bound later. Okay? But as long as we keep our cool and don't freak out about the fact that it's Lagrange error bound, and remember that we just need to know our formula, okay, we're going to be able to reliably collect the points on these. Okay. Now, then they're also saying f of x is sine of x squared plus cosine of x. Okay, now that's interesting. Okay, we're going to write that, see where this is going. We're probably going to build up a Maclaurin series for this function f. So we're going to start with sine x. Sine x starts with x because sine of 0 is 0, and it's got all the odd power terms. X to the 3 over 3 factorial. It does also alternate because sine and cosine are both alternating series. 5 factorial minus x to the 7 over 7 factorial. They ask for 4 non-zero terms, and since I said it's equal, I should probably do that. Then sine of x squared, that's going to be equal to, just replace x with x squared. Me personally, I'm going to actually, say x squared cubed. That's going to be x to the 6th. But if they're not asking for a general term, maybe we might not need to simplify it if you don't want. Okay, 2 times 5 is going to be 10 over 5 factorial minus x squared to the 7 would be x to the 14 over 7 factorial, and so on. All right, and that was part A. Then we're going to write the first four non-zero terms for cosine around x equals 0, and what we just did to produce how many terms for first four for f. All right, so I was thinking I would just move this down here so I can have that in view when I need to use it later. All right, so cosine x, the Maclaurin series for that is that one starts with 1, because cosine of 0 is 1, and it's all the even power terms. So 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial, and so on. Okay, and then we're going to use this one along with the other one to write the first four non-zero terms of the Taylor series for f around x equals 0. Okay, yeah, keep in mind they told us at the beginning that f equals sine of x squared plus cosine x. And so we're really just going to be adding this polynomial to that polynomial. Oh, that's nice. I think one of the, or two of the terms will have to combine. Okay, so f of x is going to equal, add them together. Okay, the constant would be 1, no x term in there. X squared minus half of an x squared would be positive 1/2 x squared. Okay, the next term would be the fourth power term, x to the 4 over 4 factorial. And then the next one would be the x to the 6 term. And now I'm seeing 3 factorial, that's 6, but 6 factorial, that's like, I think that's 720. I really don't like the look of that. I don't want to try to get a common denominator. I'm just going to write both of them down. So minus 1 over 3 factorial minus 1 over 6 factorial. Kind of got a little ahead of myself, but that is what I'm going to be doing eventually. 1 over 6 factorial x to the 6. Okay, and I mean, I'm not sure if you're good to stop here. I have graded problems like this, but not one exactly like this where there was a combined like terms situation. Me personally, I would want it to be just 4 terms. Okay, so even though I know that's AP Calculus and we really don't have to simplify, this I feel like might need to be, like, I might need to do something with it. So what I'm going to do is I'm going to factor out the x to the 6 and just keep the coefficients inside the box. Okay, there we go. And that's going to be the first 4 non-zero terms of the Taylor series for f around x equals 0. Okay, now we're going to find the value of f's sixth derivative at x equals 0. Okay, and in order to do that, we're going to want the 6th power term from the Taylor polynomial. Fortunately for us, we did see that there was one. So the value of f's 6th derivative at 0 divided by 6 factorial, go back to the recipe for the Taylor series, multiplied by x to the 6, that's going to equal the x to the 6th term in the Taylor polynomial for f, right there. Okay, so that's going to be negative 1 over 3 factorial minus 1 over 6 factorial x to the 6th. And then from here, what we can do is we can just kind of divide both sides by x to the 6th and start solving at what we're looking for, f's 6th derivative at 0. That's just going to equal 6 factorial multiplied by this number over here. Okay. I thought there was going to be, I thought this was the one that had like explain why f prime doesn't have a point of inflection. But maybe it does. It's a different one. I guess what we can say about this one is, oh, not a lot, because it skips the, oh wait, no, that's 1/2 x squared. Okay, I would have lost the point there. I had not noticed. All right, 1/2 x squared plus x to the 4 over 4 factorial. Okay, yeah, this one would be having a local minimum at x equals 0, but that's probably about all we could say there. Okay, now the last one, there's the Lagrange error bound question. Okay, notice they did not give us, the words Lagrange error and bound, but they did give us a picture of the absolute value of a higher order derivative, and I think that's clue enough, personally. Okay, now what I'm going to do is say, okay, using the information, show that this, with a 4th degree Taylor polynomial, okay, so n equals 4, then it's centered at x equals 0, so c equals 0, and we're approximating the value of f of 1/4, so x0 equals 1/4. And so, we're always going to start off this absolute value of the difference. That's talking about the difference between the approximation for f of 1.4 that you would get from that 4th degree Taylor polynomial, and then f of 1.4 is the true value. The absolute value of that difference, that is the error. So we're just going to say error always starts off with error is less than or equal to, because we compute error bounds in this course. So it's going to be a fraction. It's some number m, and I'll give you a little bit of explanation on that because it's been a couple of weeks now, what I'm looking for, but I wouldn't recommend writing that down on the paper. My personal recommendation is that you go for the point that it earns you the credit for the form of the error bound by having the correct error bound. Okay, I think that's going to be best for us. Divided by the next factorial, we use a 4th degree polynomial, the next factorial would be 5 factorial. And then the absolute value of x0 minus the centering point, so 1/4 minus 0 to that 5th power. Now, this m, this thing here, this is going to be equal to the maximum possible absolute value of that next derivative, so maximum absolute value of f's 5th derivative on the interval between x equals 0 to x equals 1.4. Not 1.4, 1/4. Okay, so we're going to need to go find that from the graph. Right, so we're looking at the graph here, and we're looking for the absolute value of f's 5th derivative, maximum of that over 0 to 1/4. Well, that's 1/4 right here. So we're only looking between these two red lines. Okay, and I don't know what the maximum value of the function is, but I do know that that maximum value is below 40, and 40 is a number that is printed on the paper, which means that it's going to be what we need to use. Okay, if we look at the problem closely, what's going to happen is, even though that maximum is less than 40, if we use 40, we're still going to be able to show that this value is less than 1/3000. That's kind of the consolation. It's like, and I don't think I ever really noticed that subtlety until this year. The ones where you have to use some nearby number that's slightly larger, they are always giving you something to show it's less than. Okay, now I'm going to just get rid of this because you don't want to write that down and be wrong, and that's so often what people end up losing credit on, is kind of like a form of it, and we can get the form by just going for it and just saying, all right, right here, this was 40. Okay. And now we're showing that that's less than 1/3000, and we're going to do that by doing that. Okay, we're just going to go for it. We're going to trust ourselves. Now, if we've got extra time, which I do because I have 45 minutes for this and I'm sitting at 33 minutes on this video, okay, I can go and check my arithmetic. I still got 12 minutes left and I'm talking through the whole thing. I think I can spend one of those 12 minutes, looking at this and the other 11 napping or whatever. So 40 over 5 factorial, 5 times 4 times 3 times 2, and then 1/4 to the 5th power. So that's going to be 4 to the 5th, and I might just leave it at that. Okay, now 40. I might need to write that instead of 40 as 4 times 10, but I might call 10 5 and 2 so I can start to cancel stuff off. Okay, so first thing, get rid of the 4s, then maybe the 5s, then 2s. Okay, and that's equal to 1/3 times 4 to the 5th. Well, what do you want to bet? 4 to the 5th is somehow clearly bigger than 1,000. Okay, well, I don't really know 4 to the 5th like that as a number. So I'm going to say, okay, well, 4 to the 5th, you can think about that as a power of 2. 4 is 2 squared. That's going to be 2 to the 10th. maybe you know 2 to the 10th is 1024, or maybe you just kind of like think about it, 2, 4, 8, 16, 32, 64, 128, 256, 512, and then 2 to the 10th is 1024. So 1 over 3 times 1024 is indeed less than 1 over 3000. Okay, like that. Okay, and so now I feel good about that error bound, being what they wanted me to show, even though the true value of the error is definitely less than that. Well, that's what we were showing. That 40 was a bit of an overestimate of the maximum, but that's okay. We still showed what we needed to show. All right, so that's going to be all for this problem set, right? Yep, that's it. That's it for this video. Thanks for watching.